In general relativity, the van Stockum dust is an exact solution of the Einstein field equation in which the gravitational field is generated by dust rotating about an axis of cylindrical symmetry. Since the density of the dust is increasing with distance from this axis, the solution is rather artificial. But as one of the simplest known solutions in general relativity, it stands as a pedagogically important example. Derivation. One way of obtaining this solution is to look for a cylindrically symmetric perfect fluid solution in which the fluid exhibits rigid rotation. A simple ansatz corresponding to this demand is expressed by the following frame field, which contains two undetermined functions of. To prevent misunderstanding, we should emphasize that taking the dual coframe gives the metric tensor in terms of the same two undetermined functions. Multiplying out gives we compute the Einstein tensor with respect to this frame, in terms of the two undetermined functions, and demand that the result have the form appropriate for a perfect fluid solution with the time-like unit vector everywhere tangent to the world line of a fluid particle. That is, we demand that this gives the conditions solving for and then for gives the desired frame defining the van Stockum solution. Note that this frame is only defined on properties. Computing the Einstein tensor with respect to our frame shows that in fact the pressure vanishes, so we have a dust solution. The mass density of the dust turns out to be happily, this is finite on the axis of symmetry, but the density increases with radius, a feature which unfortunately severely limits possible astrophysical applications. Solving the Killing equations shows that this space-time admits a three-dimensional abelian Lie algebra of Killing vector fields, generated by here, has non-zero vorticity, so we have a stationary space-time invariant under translation along the world lines of the dust particles, and also under translation along the axis of cylindrical symmetry and rotation about that axis. Note that unlike the Gödel dust solution, in the van Stockum dust the dust particles are rotating about a geometrically distinguished axis. As promised, the expansion and shear of the time-like geodesic congruence vanishes, but the vorticity vector as this means that even though in darker moving chart the world lines of the dust particles appear as vertical lines, in fact they are twisting about one another as the dust particles swirl about the axis of symmetry. In other words, if we follow the evolution of a small ball of dust, we find that it rotates about its own axis, but does not shear or expand. The latter properties define what we mean by rigid rotation. Notice that on the axis itself, the magnitude of the vorticity vector becomes simply the tidal tensor is, which shows that observers riding on the dust particles experience isotropic tidal tension in the plane of rotation. The magnetogravitic tensor is an apparent paradox. Consider the thought experiment depicted in the following figure, in which the inessential coordinate has been suppressed. This figure depicts a thought experiment in which an observer riding on a dust particle sitting on the axis of symmetry looks out at dust particles with positive radial coordinate. Does he see them to be rotating, or not? Since the top array of null geodesics is obtained simply by translating upwards the lower array, and since the three world lines are all vertical, it might seem that the answer is no. However, while the frame given above is an inertial frame, computing the covariant derivatives shows that only the first vanishes identically. In other words, the remaining spatial vectors are spinning about. Thus, to obtain a non-spinning inertial frame we need to spin up our original frame, like this, where Q is a new undetermined function of R. Plugging in the requirement that the covariant derivatives vanish, we obtain the new frame appears, in our moving coordinate chart, to be spinning. But in fact it is gyrostabilized. In particular, since our observer with the green world line in the figure is presumably riding a non-spinning dust particle, he in fact observes nearby radially separated dust particles to be rotating clockwise about his location with angular velocity a. This explains the physical meaning of the parameter which we found in our earlier derivation of the first frame. It is worth remarking that the null geodesics spiral inwards in the above figure. This means that our on-axis observer sees the other dust particles at time-lagged locations, which is of course just what we would expect. The fact that the null geodesics appear bent in this chart is of course an artifact of our choice of comoving coordinates, in which the world lines of the dust particles appear as vertical coordinate lines. A genuine paradox. Let us draw the light cones for some typical events in the Van Stockum dust to see how their appearance depends on the radial coordinate. As the figure shows, the cones become tangent to the coordinate plane, and we obtain a closed null curve. Note that this is not a null geodesic. As we move further outward, we can see that horizontal circles with larger radii are closed time-like curves. The paradoxical nature of these CTCs was apparently first pointed out by Van Stockum. Observers whose world lines form a closed time-like curve can apparently revisit or affect their own past. Even worse, there is apparently nothing to prevent such an observer from deciding, on his third lifetime, say, to stop accelerating, which would give him multiple biographies. These closed time-like curves are not time-like geodesics, so these paradoxical observers must accelerate to experience these effects. Indeed, as we would expect, the required acceleration diverges as these time-like circles approach the null circles lying in the critical cylinder. Closed time-like curves turn out to exist in many other exact solutions in general relativity, and their common appearance is one of the most troubling theoretical objections to this theory. However, very few physicists refuse to use general relativity at all on the basis of such objections. Rather, most take the pragmatic attitude that using general relativity makes sense whenever one can get away with it. Because of the relative simplicity and well-established reliability of this theory in many astrophysical situations, this is not unlike the fact that many physicists use Newtonian mechanics every day, even though they are well aware that Galilean kinematics has been overthrown by relativistic kinematics.